We'll continue looking at the natural log function today, and we're going to keep going with that pattern of looking for the function, a fraction where we have the function here and the derivative here, to help us see that we're going to use the natural log to find our answer. So we'll start by looking for some trig identities and showing you where their formulas come from. So the first one we're going to use is tangent. Now, if you were to see the actual answer to this, you might wonder, how the heck did you get that answer? But the way we've done it is we've rewritten the integral for tan x using probably the most common identity that you have been working with. So now I would remember there's a connection between sine and cosine, and I can rewrite this like the integral, and this is my function then on the bottom, and this would be my derivative on the top. So if that's my derivative, you have to ask yourself, am I missing a constant? Is this the derivative I'm looking for, or is something missing? And the answer is yes, something's missing. The derivative should be negative sine x. So to balance it out, I'm going to have to put a negative here. So I'll rewrite our problem now as the negative sine of x over cosine of x. And I can integrate this using natural logs. And the function is cos x. So that's how you end up integrating the tangent function, and natural log is a part of that. So we'll try it again just to show you the secant graph. Secant also has a strange antiderivative that you might wonder how on earth we got that, but it's using logs. So the secant of x, now this isn't really an identity, but what I'm just doing is I'm multiplying it by a fraction that's an equivalent. So secant x plus tan x divided by secant x plus tan x. I haven't actually changed the original expression. Now, it's not really something you'd expect to come up with this creativity on your AP exam, but it's certainly something creative here. It's a clever trick, because now secant squared x plus secant x tan x is on the top, and on the bottom I have secant x plus tan x. And if you look, this secant x has a derivative of secant x tan x, and the tangent graph has a secant squared. So both of them are actually up there. We have the function here and its derivative here. So that means I can just use the natural log of secant of x plus tan x. So here's the remaining of the trig identities. And again, we don't have a formula sheet in our class for the AP exam, so unfortunately those are ones that I'll expect you to know about. But you might also see them in other forms, like this next example here. The integral from 0 to pi over 4 for the square root of 1 plus tangent squared x dx. That's the same thing as if you use your identity, 0 to pi over 4 of secant squared x dx, which is the integral from 0 to pi over 4 of secant x dx. And we just worked that one out. So that'll be the natural log of the secant of x plus the tangent of x, evaluated at 0 and pi over 4. So then we can work out a numerical value here. That's going to be the natural log. And secant of pi over 4, that's 1 over root 2. And tangent of pi over 4 is 1. Excuse me, that's the cosine. It should be just root 2. And the natural log of secant 0 is just 1. and tangent of 0 is 0. So that gives me natural log of root 2, take away natural log of 1, and I guess we would probably write that as 1/2 the natural log of 2, and natural log of 1 is 0, so that's our answer. Okay, so for the next one we're going to find the average value, and just a reminder, the way that works is the average value is going to be, well, this should actually say, I guess to be more specific, this should just say the average value of tan x on 0 to 4. So it'll be 1 over pi over 4 minus 0, the integral from 0 to pi over 4 of tan x dx. So I end up with 4 over pi and the integral from 0 to pi over 4 of tan x dx. So this is going to be the negative, I guess we might as well call it negative 4 over pi times the natural log of the cos x from 0 to pi over 4. Maybe I'll write it in a different color just so we don't get into the previous question there. So this will be negative 4 over pi, and I'm going to be looking at this from, let's see here, cosine of x, so it'll be cosine of pi over 4, take away the cosine of 0, so the cosine of pi over 4 is 1 over root 2, and the cosine of 0 is 1. And I'll probably multiply by root 2 over root 2 here, just to get a rationalized in my denominator. So this will become, let's see, negative 4 over pi. I'm going to have to move that down, I'm running out of space here. That'll be negative 4 over pi, and I'm going to get, let's see here, that'll be root 2 over 2. So I just rationalize that denominator. If I make a common denominator, then I'll have root 2 minus 2 over 2. And that means I can simplify this out a little bit. I get negative 2 over pi times root 2 minus 2. And that should be good enough for our answer. Okay, so we should go back to practicing looking for this pattern again of a function and its derivative. So, you know, when you come across something like this and you can't seem to decide where the function and the derivative are, it's good if you split things up. So that's what we're going to start with here to help you see the difference. Instead of that question, what I'm going to say to do is think about it if it was this question. Okay, so there's a couple of things that we're looking for here. I mean, I guess maybe I'll rewrite it one more time for you. But multiplying like that would be the same thing as having 1 over x on the top and the natural log on the bottom. So now I have that pattern again where this is the derivative and this is the function. Sorry, that should have been a 2 there. So as soon as you spot that pattern, then you can apply the natural log as your antiderivative. So we're going to have the natural log, and this is a bit of a funny one. It's the natural log of the natural log x. We're evaluating at e and e squared. Suppose I'll have to change one more time here. So this will be the natural log of the natural log of e squared. Take away the natural log of the natural log of e. So natural log of e squared, that's just going to be 2. Natural log of e is just going to be 1. So natural log 2 minus natural log of 1. Natural log of 1 is a 0. So I end up with just natural log of 2. So again, looking this way, we're going to see that there's, in this next question here, for solving this differential equation, hopefully you recognize it right away and you're getting the hang of this pattern. There's a derivative and a function, so if they're matched up that way, I know I'm going to be using natural log to answer this question. To solve this differential equation, I need to have all the x's on one side and all the y's on the other. And what I'm going to have is dy equals 2x over x squared minus 9 dx. And I can't remember if this is the first time we've talked about differential equations or not, but now what I'm able to do is if I integrated both sides, then I'm able to solve for what the original conditions were. So here, what I'm going to have, the left side's quite simple. The integral of dy is just y. And the integral on the right side is, it's not too bad. We've been practicing natural logs right now, so it should be fresh in your mind. But this is going to be the natural log of x squared minus 9 plus some constant. So we end up with this differential, the solution to the differential equation. But we were given an initial condition, so we can actually find out what the constant was. Because we know that this was an initial condition in the function that we started with, that means I can substitute in for x and y. So what I'm going to do here is I'm going to put in 4 equals natural log of 0 squared minus 9 plus some constant. So 4 is equal to the natural log of 9 plus c. So my constant is going to be 4 minus the natural log of 9. So the particular solution that I'm looking for here should be y equals the natural log of x squared minus 9 plus 4 minus natural log 9.